Okay, so hello everyone. We are very happy to have Omri Ben-Eliezer with us today. Omri did his master's and PhD here, so we probably seen him with Alon. Before that, he was at the technical, studied mathematics and computer science. Since then, he joined for a quick period the Weizmann Institute, I think 2 months, and then Harvard, and now MIT. So Omri's interests are quite wide. He's doing streaming and sublinear-time algorithms and studies social networks, but I guess we'll hear about it now.
Thank you so much, and thank you so much for the invitation. I'm very happy to be here today. It's great to be back. Today I'll talk about fast algorithms and complex environments. So almost every aspect of our modern human life involves continuous interaction with huge and complex computational environments. And this, of course, creates a large number of algorithmic challenges. For example, we live in a data-driven world. The amount of data that we need to process quickly increases all the time. Data becomes more complex, more interconnected. But scale is not the only challenge in modern computational environments. The type of environments that we engage with algorithms or with algorithms engage with each other become more and more interactive, more and more adaptive. The feedback loops are shorter. You will see some examples of such environments that kind of arise in modern computing. And because of the ever-increasing involvement of algorithms in our everyday life, we have new requirements, new societal requirements. For example, we want them to maintain the privacy of users, privacy of data. We want them to be robust to adversarial attacks, robust to distribution shift, and so on. We want the decision that they make to be fair. So they take an ever-increasing role in our society, and we have requirements that from them as a central player in this sector. And in my research, I work on the design and analysis of, I would call it probably fast algorithms in modern complex computational environments. And a lot of my work involves also computational modeling, so trying to theoretically or mathematically model the kind of challenges and issues that arise in modern complex settings. By fast algorithms, I mostly refer to algorithms that use a bounded amount of computational resource. So for example, streaming algorithms use small amount of space. Algorithms take small amount of samples or small amount of adaptive queries. And I would argue that there is a very nice symbiosis between the design and analysis of algorithms and the modeling effort for complex environments. And I think it goes both ways. So on one hand, it's obvious that to design algorithms that are useful and relevant for modern settings, we need relevant models. But as I will try to show during this talk, there's also a lot to learn from the algorithmic perspective. So there's a lot of, in my research, it's kind of a recurring theme that from the algorithmic study of some problem, we learn many things that are completely non-algorithmic, that don't seem to be algorithmic. So there's a nice symbiosis between these two aspects. And in general, I work on a variety of fast algorithmic settings, so streaming, sampling, bounded query settings such as active learning problem testing. I also work on design analysis of randomized algorithms. And on the complex environment side, I worked also on a variety of settings and constraints. So for example, on the adversarial robustness algorithms and design analysis of algorithms under differential privacy constraints. I also worked on problems that have a complex structured data. So for example, complex networks, algorithms in complex networks, or dynamics in complex networks, structured data in low dimensions. I'm also interested in structured knowledge representation from those scales, so I have some work in the single document scale and all the way up to that society scale. And a lot of my research falls somewhere in the middle. So it has a little bit of modeling of computational environments and a little bit of algorithm design. And in this particular talk, we will focus on mostly on two fronts representative in some sense in research. One front tries to symbiosis between bounded space algorithms and computational environments that have complex dynamics in some sense. So what we will see is some of our work on adversarial robustness of streaming algorithms. And the second part of this will be most of the talk, maybe 2/3 of the talk. And the second part of the talk, I will focus on the beautiful symbiosis between bounded query algorithms and complex structured data. I will mostly focus on some recent work we had on algorithms in large real-world social networks. And along the way, I will try to show you some of the recurring themes of my research. So first of all, it tends to be, even without intention, it tends to be multidisciplinary. A lot of the models that we try to investigate end up connecting in different areas of computer science, and sometimes even between computer science and other disciplines. There's a lot of beyond space models and analysis, and as I mentioned, a lot of the times there are new structural insights that arise from the algorithmic style of programs. So in the first part, I will talk mostly about adversarial robust streaming, and in this context, mostly about our work with projects around David Woodruff and Elon Negev. I will also mention some other work in this front, also on adversarial robust sampling in a streaming setting. And I think that the most apparent recurring thing here will be of multidisciplinary. Okay, so let me start with the classical model of streaming. So in the classical model, this is a simplified version of the streaming model, what you will see here. So in the classical model of streaming, we have two pairs, the world, which provides us with a data stream, and the algorithm. And the world sends data updates one by one to the algorithm. And the algorithm needs to process these updates immediately. So after it receives the update, they are thrown away. And the goal of the algorithm is to compute, or approximately compute, one approximation, after some function, some useful function over the string. So for example, if we think about an algorithm that sits on a network router and tries to understand how many different IP addresses we have in the network, then counting the number of distinct elements is useful. There are many other useful kind of functions that we may want to compute. So for example, the set of indicators, the norms, entropy, and so on. There are many examples. And the catch here is that we want the algorithm to be space efficient. We want to use as little space as possible, as little memory as possible. Okay, so the model is as follows. In each round, the world sends some data update, and then the algorithm processes this data update. Okay, so see two examples of this. This goes on and on for streams of length n, so n is some large number. And streaming has a lot of applications in a multitude of areas within computer science and even outside computer science, even maybe in natural context in some sense. So because streaming algorithms work with a small amount of space, they fit modern computer architectures very well. So they can run in cache, and just the fact that many of them can run in cache can increase the time efficiency by orders of magnitude compared to other types of algorithms. So they are very efficient in a variety of contexts, such as databases, cloud computing, computer networks, data series analysis, monitoring. But they also, I would argue that they also play a role, for example, in our own brain. So it is very well known, there are very well known experiments in cognitive science literature that show that in kind of short-term context, our memory is extremely limited. So if you ask people to memorize a sequence of digits, the amount of digits that they can memorize is more or less 7. So it's a very bounded memory setting. And we also need to understand this kind of numbers. Okay, back to the streaming model. So since the streaming model, since the systematic investigation of the streaming model started roughly in the late 90s, so there's a work of Nobel, is one of the works that started this field. And Nobel, of course, other collaborators, some of them also colleagues. I love the Matthias Segedin, also Matthias. And then since this area started, basically there was a lot of effort trying to develop very efficient, even optimal randomized streaming algorithms for a variety of the most important problems in the streaming literature. And I would also like to comment that deterministic algorithms are known to be exponentially less efficient, in particular for all of these problems and also for many other problems. So somehow it's interesting to study mostly randomized algorithms in this context. But there was one problem with this line of work. The proofs of all of the results that are mentioned here assume that the stream is fixed in advance. Okay, what do I mean by that? So I mean that basically the proofs implicitly assume so they say something like this: for any stream x1 up to xn of updates, we have a guarantee, we have an approximation guarantee of so and so for approximating a certain function. And this is not always realistic. It might be the case that future updates that the stream will send us, that the world will send us, will depend on previous outputs of the algorithm. So let me formally define the adversarial model. Basically, it's a model where we have a feedback loop. So, for example, here the adversarial world sends us the first data update, and then we process it, and then we immediately provide an output to the adversary. And then the adversary stores this output for the rest of the line, for the rest of the stream. And the next update that the adversarial world will send the algorithm, will depend on what they receive. So there is a feedback loop. So this setting does capture adaptive players. Obviously, it captures all sorts of adaptive players, in particular also fully adversarial players that can see our outputs. And so I call it an adversarial model because we think of the world as a strong, knows the entire history of outputs. We don't assume computational constraints on it and so on. It just doesn't know the internal state of our algorithm. And the goal of the algorithm is to maintain a multi-cyclic approximation in this challenging adaptive setting. And this is a two-player game, so the goal of the world is to break this multi-cyclic approximation. Okay, and I told you a couple of slides ago that existing analysis of randomized algorithms break down in this adaptive setting. But it's not just the analysis, it's also the algorithms themselves. So by now we know about many of the most important algorithms in the literature that are probably not robust in adaptive and adversarial settings. And in some of these works, there are some mitigations, there are some ways to modify the algorithms in order to make them more robust. Some of the cases we don't know such mitigations, but we can't, in general, we can't trust the guarantees that we have for randomized algorithms in adaptive settings. And let me present to you now two examples of adaptive settings that, where we clearly need robustness, clearly need to be robust against adaptive behaviors. So the first example on the left is related to, is truly adversarial in the sense that this is an example of two security researchers from Germany attacking a server and causing a denial of service attack because basically the algorithms that the server used were not robust. The example on the right is, I would say, beyond adversarial. It's certainly adaptive, but the players don't really try to break anything, but they are clearly adaptive and try to optimize something that may be undesirable for the algorithm. So on the left, the example on the left shows basically an attack, an adaptive attack on a server that used a weak hash function, a hash function with a small amount of randomness. And after some small amount of adaptive interaction with the server, the security researchers were able, because it's a hash function, so if you direct the traffic to the wrong locations, you don't have good guarantees on the running time of things. So they were able to basically overcrowd certain parts of the hash table, and this created a denial of service attack on a huge server with hundreds of thousands of cores, and they did it with relatively little communication. So this is an example of an adversarial setting where we clearly would have wanted the server to be robust to this kind of adaptive interaction with the researchers. But there are numerous settings in our modern world that are adaptive, maybe beyond adversarial, where we also want robustness. So suppose, for example, that you have your own website and you wanted to appear in the first as the first result in Google when people search for the relevant queries. So what you can do nowadays is you go to a person that specializes in search engine optimization, SEO. They're actually people whose day job is to do SEO. And what they do is to provide you with tools to optimize your the appearance, the statistics of your website in order to appear in higher locations in the search engine. And so basically these people know the Google algorithm very well. They are probably adaptive. They know how it updates, what kind of changes they do along the way. And so on the other hand, Google also needs to update its algorithm on the other direction. So the search engine also needs to update its algorithm on the other, and in order to not unfairly favor those players that are more strategic. So it's kind of a game theoretic situation where the agents want to optimize one thing and Google wants to optimize another thing. And on the other hand, the amount of data that Google processes is huge. They definitely need to, for example, use sketch representation for things. So they definitely need to run some streaming algorithms or something that compresses things along the way. So we need to provide guidance for Google on how to maintain the robustness of their algorithm in this challenging adaptive scheme. And one can ask whether, so we know that randomized algorithms, classical randomized algorithms, are not guaranteed to be robust in this adaptive setting. So that they do not work in general when we have feedback loops. And we also know that the deterministic algorithms are just not efficient. They are always robust, but they are not efficient. And one could ask whether we can have both robustness to adaptive behavior and efficiency. So can we have kind of near randomized efficiency with near deterministic robustness? And what we were able to show, this is in the work with Rajesh, David, and Elon, is what we were able to show is that for all of these important problems in the streaming literature, in a streaming model that is called the expression-only model, we indeed have this. It's possible to have algorithms that are both space efficient and probably robust against adaptive behavior and in particular adversarial behavior. And this sort of created a paradigm shift within the field of streaming algorithms and sometimes also in related fields. So if before our work, people mostly focused on two settings in streaming, either the randomized setting where you want to be correct on a fixed stream, or in the deterministic setting where you always provides robustness. Basically, we show that there is also a middle ground. There's another model that requires attention. This is the adversarial robust streaming model. And since then, there was a lot of research on a variety of fronts that are related to adversarial robust streaming. So, for example, there was several beautiful and more sophisticated frameworks. So our result basically, the results that we saw are basically special cases of a framework that we developed. And then So, and there was a number of beautiful and sophisticated frameworks that improved upon our framework in certain ways. There was quite a bit of work on the adversarial robustness of specific algorithms in the literature. I would like to point out this work from 2013. This is by Hart and Woodruff. And they were able to show that linear sketching, which is maybe the most important technique in streaming, is not adversarial robust. But maybe because the result was negative, this didn't encourage researchers to try to look more into this topic. And in some sense, our result was the first to give a positive result in this setting. And there was also a lot of study of robustness in related settings, in a variety of graph algorithms, ML settings of certain types, cryptography, and so on. And there's also some work on separations and lower bounds. So there are specific properties for which we know that there are separations between the adversarial setting and the static one. Although we don't know much, we know about specific results, but we don't know much about, for example, all of the problems that I mentioned to you in the previous slides. Okay, let me now try to present to you our framework and what it is based upon. It's really simple. I hope you will be able to understand it fully. The ideas are really simple. It relies on a new notion that we developed that is called the flip number of a function. Before presenting what flip number exactly is, I want to tell you what the framework is. So let's say that we have an algorithm that works in the static setting. So any algorithm that works for one epsilon approximating a certain function f. And it needs to provide a mild technical condition called tracking, which basically means that the output is always at any given time is correct. And from this algorithm, our framework provides a new algorithm where the space complexity is the flip number of the function f that we want to compute times the space of the original algorithm. And the new algorithm is provably adversarially robust. Okay, now I still need to explain to you what is this flip number. So the flip number of a function over a string of lengths m, given an approximation parameter epsilon, is the maximum number of 1 plus epsilon, 1 plus minus epsilon multiplicative changes in the function that we can have over a string of lengths m. So if, for example, so here you see an increasing and non-increasing monotone function, and if we have so basically here the flip number will be bounded by the log in base 1 plus epsilon of this value divided by this value. So for example, if we want to count the number of distinct elements in an insertion only setting, so the number of distinct elements only goes up, and the flip number turns out to be of order log n over epsilon. And this is the overlay that we got over the static setting. Okay, and now to give you some idea about how a framework works, I would I would like to show you this picture. So the main idea is that we run flip number many copies of the algorithm, and we switch between them from time to time. So each time we have an update that enters the stream, we send it to all of the copies. So all of the copies update their state simultaneously. But we only have 2 copies that actually interact with the adversary in some sense, and all the other copies act in the background. They don't provide anything meaningful to the adversary, and so in some sense we can think of them as static copies for the time being. And the idea is as follows. So we have 1 copy that provides the output to the adversary, and once it gave the output for the first time, this output freezes for the rest of the interaction. And we have another copy, the active copy, which determines at which point the frozen output is no longer relevant, is no longer a good approximation. And what we are able to show is that, and then once this active copy determines that the frozen output is incorrect, then they switch. The active copy becomes the frozen output one, provides an output, and then we take a future copy, and this one becomes active. And what we are able to show is that the only guarantees that we need to satisfy here is that each active copy, in the time that it is active, is correct on a specific stream, in a specific stream that we can think of as bounded, as fixed in advance. So this is exactly the static guarantee, and we just need to apply the static guarantee on all of the copies of the algorithm. And this creates a new adversarial robust algorithm. Okay, so this is our framework. The space complexity overhead of our framework is linear in the flip number. And subsequently to our work, there are several other frameworks that obtain improved guarantees. And all of these guarantees are a function of the notion we developed of the flip number. So there was a very nice use. So most of these works, 3 of these works, are by Elgorithmic researchers. So one of the frameworks was based on differential privacy. Usually, differential privacy is used to preserve the privacy of users of data and so on. So here, they found a way to protect the data, the kind of internal state of an algorithm using differential privacy. And there was also another beautiful framework based on difference estimators, a new notion in streaming that also solves some all the open problems in a sliding window model. And there's also a framework that combines the best of both worlds. But you can see that the best dependence in the flip number in all of these frameworks is of order square root lambda for the flip number. And one can ask whether we can do better. So the answer is that in general is no. There is a specific problem that comes from the adaptive data analysis literature that shows that the separation between static and adaptive could be as bad as square root of the flip number. Okay, but all these results depend on the flip number, and one may ask whether the flip number, yes.
Can you give some intuition about why you never run out of the hidden copies?
I need to know in advance how many copies we have. Why there? Because
you generate the copies. You start a certain number of copies. Can you give an intuition of why you never run out, even though you sometimes have to switch to a fresh one?
Yes, because each switch basically happens only when the value of the function changes by a multiplicative factor. And the flip number captures exactly that. The flip number captures how many multiplicative changes we can have in the output. So no, it's a function of it's a parameter that depends only on the function, not on the output. Okay, so back to this discussion, all of the dependencies we have are directly depend on the flip number, and one may ask whether the flip number is always the right parameter when you switch from the static setting to the adaptive one, and the answer is no. So for the insertion deletion setting of streaming where we allow both insertions and deletions of elements, the flip number can be as bad as the length of the stream, and this is what's possible. But we were able to get algorithms for some certain important problems in the literature with dependence that is significantly better than the square root of the flip number. The idea there was a combination of the differential privacy framework with some results from the sparse recovery literature that are robust to adaptive settings. And also this is the best known result for insertion deletion schemes. So, unlike many other settings in streaming where we know that the space complexity that is polylogarithmic in the length of the string and the size of the universe is achievable, and in particular for insertion deletion streams in the static setting, we have polylog type bounds. Here the best bounds that we have are polynomial in the length of the string, which is far from ideal. So trying to understand, and we also don't have good lower bound for these specific problems. So one of the central open problems in this field, in our field, is to try to close this gap. Yeah.
So if I understood correctly, your algorithms they only work for the only addition model, right? And no deletions. And the counterexample is addition and deletions, right?
So the algorithms work it's a generic framework that depends on the flip number of the problem. The flip number tends to be small when functions go up, so the insertion on the model is small. And the subsequent frameworks even get better dependencies. So they are near optimal algorithms for using the better frameworks. But then when the flip number is large and square root of flip number dependence is not very helpful. Okay, so this exponential gap between adversarial streams and static streams, or between adversarial streams and the lower bounds are certainly an important open problem in the literature. And I think my favorite future direction that I would like to investigate more, which is kind of a part of a broader initiative that I have, is to try to understand good beyond worst case models in these adaptive but not fully adversarial settings. So for example, suppose that we have a user that interacts with the database. So a user is, in most of the situations, is not fully adversarial. It is adaptive. I mean, the next queries, the future queries that the user will make definitely depend on what the database, what kind of information the database provides. But the dependence is not adversarial. And on the other hand, we know a lot about humans. I mean, there are many areas in science that investigate the capabilities of humans. So there's a very nice notion from game theory, for example, of bounded rationality, that basically says that humans are kind of streaming algorithms themselves, and they are not even fully adversarial. So they kind of make decisions based on a very bounded context. And I'm very curious to see what kind of results we can have in this adaptive setting under more concrete assumptions on the way that the stream is generated. So, for example, when can we have robustness for free? And to finish this first part of the talk, I would like to mention some other work that we did on this front on sampling in adversarial robust sampling in a streaming setting. Here, the objective is a little bit different. So, suppose that we have a family of multiple statistics that we want to approximate over the data stream. And we ask, what is the sample size that we need to take in this adversarial world to have uniform convergence, so that each statistic in the data will be represented up to an error of epsilon by the frequency in the sample. And I think many people in the audience will realize, so uniform convergence is a condition in statistics, and many people in the audience may realize that it is connected to pack learning. So uniform convergence implies pack learning. And in our work, we were able to characterize, to obtain, so we first provided the first model for a sampling in an adversarial environment, which actually it actually preceded the work on adversarial robust streaming and inspired it. And in a subsequent work that we had on this front, we were able to obtain optimal sample complexity bounds. It turns out that the Littlestone dimension is the right parameter. And along the way, we also obtained optimal regret bounds in online classification in a pack setting, in online learning in a pack setting. And from technical perspective, we bounded both of these. So it's known that online learning in this setting is captured by what is known as the sequential radiometric complexity. So we were able to bound also the sample complexity in our setting by the same complexity. And we developed a new notion of fractional online covering that to get better bounds for this sequential radiometric complexity. So it solved both problems together. So as you can see, we saw two settings. One related us to online learning. The other setting related us to another set of techniques from different areas. And it's kind of a recurring theme in this adversarial robust world, that it connects streaming with a variety of different areas in computer science. Okay, so this is what I have to say about the first part of the talk. And in the second part of the talk, I would like to tell you about some recent work we had on algorithm design in large social networks. And this is of my interest in the interaction between bounded query algorithms and complex structured data. So, and this is joint work with Talia Eden, Yoel Owen, and Dimitris Pakis. So the setting that we investigated is as follows. Suppose that we live in a large real-world social network. So now the setting is more practical. You're going to see empirical results. We're not going to see theorems. And the setting is as follows. We started a random node in a large social network, and we can use a limited amount of queries to the network. And the queries that we use are called the neighborhood queries. Basically, you can ask, you can apply the query on a certain node, and it returns the list of neighbors on this node. And our goal is to kind of explore the network as quickly as possible, using with as few queries as possible to explore the network as well as possible. So the concrete application that we wanted was to be able to sample k almost uniform, almost independent random nodes in the network. So formally to simulate a distribution over k tuples of nodes in the network that is epsilon close in TV distance to the completely uniform. And the ability to sample random nodes in a network is central to almost any algorithm that you can think about in statistics over networks, in web mining. For example, the pager algorithm with its variants use teleportation. Teleportation is basically takes a new random sample, and to support the pager algorithm in a bounded query setting, we need to sample a large set of. Okay, so here you see several examples of neighborhood queries. Each time we see a new neighborhood of a new vertex.
Can you say again, what do you mean by you gave a definition, but I couldn't follow. What is to explore the network? What is your formal definition of exploring the network?
Yes. So the formal definition is we want to return k. Okay, the semi-formal definition is that we want to return a large set of more or less random nodes in the network of k almost uniform, almost depends on nodes in the network. The fully formal definition is I want to return to simulate a distribution over k tuples of nodes in the network that is epsilon close in TV distance to the fully uniform distribution to M2 scale. Okay. And I would like to say that neighborhood queries are natural in this context. For example, they are supported in the Twitter API, and they are supported in the APIs of many of the largest real-world social networks. And this is also the way kind of we explore this kind of settings. For example, our profile is one node in the network, and we can go to we can see the friends list of ourselves, of our friends, and so on. So this is kind of very nice.
Anyway,
Yeah.
and for some reason it's too expensive to just do it, right? To summon k random nodes. You can
I don't have access to it. They have only query access. It starts from the point, and
but you start on the random nodes. You start on the random node.
Yeah.
So that's the
no, I mean this is the only access that I have in the beginning, only everyone. You can also think about I mean, it's because we live in a practical setting. It doesn't matter. I mean, I can say worst case not because it's not really. Yeah, I don't know if it's as interesting as something can run. All right. So I think the first solution that we may think about is to use random walks, to use uniform random walks to repeatedly generate almost a uniform network. And this scales, so the amortized per complexity per single sample scales with the mixing time of the network. So this result is for a bounded degree flux. And turns out to be necessarily sufficient. But the problem is that the mixing time of social networks, while it is sublinear in the side of the graph, so they do mix maybe relatively well. They are certainly not expanded, so the mixing time is to the order of hundreds or thousands sometimes, and so the core complexity in our case will scale to the order of hundreds maybe per sample, which might not be ideal if you want to generate a large number. But
Is the network connected?
yeah, we assume that the network is connected. Right. So we have to throw away parts that we cannot explore because our query model doesn't allow for accessibility. Okay, so the natural question is what we can do better. And we try to explore some other kind of properties that large social networks have. One of the properties is the power law degree distribution. So the highest degree nodes have very high degrees. For example, the highest degree nodes in Twitter have more than 100 millions, more than a degree of more than 100 million. But another very interesting, very attractive feature of social networks is that they have some sort of a core-periphery structure, where the core is a highly connected subgraph with most of the high-degree vertices. It is better expanding than the rest of the network, and so on. And the periphery is kind of a combination of a collection of many relatively isolated components, lower degree, and so on. And so these two areas in the network without kind of heuristic techniques, we didn't really find them, are very different from each other. So we try to understand what we can do with this structure in order to design new algorithms for this problem. And we guess that because we have this power law degree distribution, that it might be a good idea to try to first reach the highest degree nodes in the network, and to try to see what kind of structure we can have after a sublinear amount of queries achieving this highest degree vertices. And the experiments that we tried to do in the beginning try to understand how many of the engaged nodes in the network. So we only looked at nodes that are at least that have at least some degree to get some very rough approximation of those nodes that appear in the core. How many of them have a very, very high degree neighbor? And what we were able to find out is that this so kind of the core of social networks tends to have a sublinear domination number. So almost all nodes in the core have a neighbor of very high degree. And what you see here, so the results tend to get better in absolute settings, in absolute terms, as the graph grows. So for example, the largest graph that we explored was the full Tumblr graph, 250 million nodes and 15 billion edges, and there we got the best results. And also the second best was the second largest. So this is clearly some sublinear pattern that we can't fully quantify at this point, and it clearly seems a sublinear in some sense. And indeed, our algorithm uses this kind of structure. So basically, in the beginning, we do a pre-processing step that looks for the highest degree nodes in the network, and we call them L0, and that's called the neighbors of these nodes L1. This is the next layer, and our hope is that the other nodes, those that are not neighbors of the highest degree nodes, will decompose into small components, as we know happens in the periphery. And indeed, this kind of strategy works pretty well. So, for example, in a Sina Weibo, a network with 60 million nodes, we're able to get results with random walk-based algorithms by significant margins. For example, if you want to sample 0.5% of the nodes in the network, then our method has an amortized kernel complexity of something like maybe 5, 6, 7, something like this, and random walk-based algorithms have something like 50, 55. So quite a significant improvement. And I would like to, and the thing that I would like to say about on this front is that along the way we had some very nice examples where we learned something structural about the network that seems to be completely unrelated to algorithm design. So here's one example of something that looks like kind of a scaling law about that says something about the relationship between core-periphery. So as we increase the size of the core of the highest degree of the size, the set of highest degree nodes in the network, what we saw is that the average component size in the periphery basically decreased exponentially. And I think it's a very kind of interesting phenomenon of anti-expansion. Things decompose very, very easily in an exponential rate, and I think I don't know at this point. I don't know. I don't have much to say about it, but I think it's a very interesting thing to look at. And the fact that we actually have So social network data is easy to access, it's easy to work with. You can find it in the internet. And the fact that we have this kind of data to work with and derive very, very interesting and useful observations about the structure of real world data, I think very attractive. And I would like to say also that the type of core-periphery, the composition that we developed here, is not useful only in a query-bounded setting, and in an ongoing work, we are using it to accelerate the shortest path computation. So we show that for many pairs of nodes in the network, basically the shortest path goes through the core of the core, and then we build a data structure that is more efficient than the existing solution because of that, because it uses some sublinear size structure. And it's somehow reminiscent of what is called the highway dimension in road networks. So it's kind of the highway dimension. It might be something like the highway dimension social networks.
Isn't it exactly the same thing?
I don't know.
It sounds like it was short spot, it sounds exactly like it.
Yes, it might be. I'm not sure.
Maybe I missed Omri. You have formal guarantees for your algorithm that depends on the periphery structure of the.
Yeah, so we have some convincing guarantees and some non-convincing guarantees. The convincing ones are that our approach actually converges. So if you take if you do the processing well enough, it doesn't depend on the size of the zero. But if you do the processing well enough, then we actually the samples that we generate are actually near uniform. I think the non-convincing part is that we do have bounds on the query complexity per sample under certain conditions, but I don't think so. So there's a lot of work to understand exactly what happens.
In particular, do you have any kind of formal reason why this particular why would you bring the mixed type in this case? Yes, right. I mean,
Yeah. So
why
that's
would
about
the structure. No, I mean for your algorithm, right? What would be the reason for your algorithm to work better?
Yeah.
The mixed time.
Yeah, it's a mix of reasons. So one of the reasons is that a lot of the nodes in the network are just neighbors of zero. They're just not just nodes in the core, also many nodes in the periphery are neighbors of zero. And also kind of instead of looking at the mixing time of uniform random walks, we look at very specific cuts. We try to go through the hardest cuts in the network, and we try to do that explicitly. So this is where the savings come from. Okay, so I finish very soon. I just want to say one thing about the interaction between bounded query algorithms and complex structured data. So a central question that I've been very interested in throughout the years is kind of what is the query complexity of understanding characteristics of data in low dimensions. So I work on these kind of problems for mostly in the probabilistic setting and recently also in active learning setting. And these kind of questions are inspired, sometimes motivated by questions that come from different areas, and sometimes there are interesting connections. So I would like, for example, to highlight one connection that we had to computational biology. So we were studying, as part of the probability testing framework, we were studying the distance of sequential data from not having some forbidden pattern. And it turns out to be useful also for example, when you want to synthesize DNA sequences without some instance. So we developed combinatorial characterizations that were later used or inspired work in computational biology. Another direction of research that I'm very interested in is kind of complexity of shape analysis. So obviously, for example, our human eye it's very efficient in the way that it classifies shapes and tracks shapes, tracks movements, and so on. And then it's also adaptive. So I'm curious about the power of adaptivity and understanding the shape of structure. So we have a recent work in the last few years on in active learning that tries to understand this question in a very simple setting of trying to learn the structure of polynomial threshold functions. Okay, this is what I have to say for today. Thank you so much. Again, I want to mention that I work on the interface between design analysis of fast algorithms and modeling, computational modeling of complex environments. Thank you.
Going back to Thomas' question. So L0 consists of very high degree nodes, but it's very far from an expander. It does have small cuts.
S0 is because it's it might be yes, but it doesn't matter for us because we just capture. This is the part of the graph that we capture completely. So.
But if I thought what your answer to Thomas was that if L0 is kind of an expander, then a random walk would work.
No, but only in S0. S0 is a small sublinear part of the network. The challenging thing is to reach L2, to reach the periphery. And the cuts that we care about most are the cuts between L1 and L2.
So it seems that your approach may be very promising for many other graph algorithms, problems. I wonder if you have any beyond the shortest path that you mentioned, what other types of graph problems in your approach help?
So I think anything that we want to care about. I mean, so there are many different contexts. So I also think I mentioned PageRank at the beginning, and computing PageRank sublinearly is sort of. I think there are some results in this one, but it's sort of an open problem to give sublinear algorithms for computing, for example, personalized PageRank, which is important. Algorithm in data mining, and this could be a promising direction, for example, to provide sublinear algorithms in this context because we very heavily use the complex structure. What we give is approximate answers, of course, because it's sublinear, but it seems to be useful in this context, and we definitely would like to see it.
And I have another question. You mentioned two models of the adversaries. One is pure adversarial, and the other is more strategic. And those are two very different models. So I wonder if you have any thoughts of how to attack these two types of adversaries.
So first of all, the results that we prove apply in both cases. They apply in any setting that we have achieved.
But for example, let's say the lower bounds, for example.
Yeah, so exactly. I'm very interested in these strategic models, trying to understand kind of how the bounds change when we have someone that is that is adaptive in some sense, but not fully adversarial. So kind of the example that I gave is for bounded humans that might be adaptive, but because it's relatively a bounded context. But in general, I think it's a very interesting question. Connects streaming algorithms with the game questions.
It's good.